I first walked beneath the Market Street Bridge in Philadelphia, whose records list construction beginning in 1873 along the Schuylkill River, expecting nothing more than standard post-Civil War masonry. An 1874 engineering journal described its arches as routine infrastructure for a growing industrial quarter. I studied an albumen photograph taken that same year, expecting crude stone alignment, imprecise symmetry, the limitations of hand-set blocks. But the inner retaining wall showed something else: granite courses cut to tolerances under 3 millimeters, aligned across spans too large for the documented derricks of the period. Behind a sealed arch, I noticed a depression leading downward, an apparent hydraulic cavity no maintenance report ever acknowledged. Some researchers now classify these submerged voids as remnants of Tartarian infrastructure, pressure regulated under arch chambers designed for purposes not recorded. I arrived expecting brick. I left unsettled, realizing the investigation had only begun. The official construction ledger from the Philadelphia City Archives lists the Market Street Bridge project as commissioned in January 1873, with completion scheduled for late 1875. The contractor, a firm called Hewson & Sons, submitted monthly reports documenting progress: foundation excavation, pier placement, arch construction. The language is mundane, bureaucratic. 72 cubic yards of granite delivered, 12 masons employed. Weather favorable. Nothing in these documents suggests anything unusual. But when I examined the earliest photographs, albumen prints from the Philadelphia Historical Society, dated October 1874, the bridge already showed features that contradict the timeline. The stone courses are not roughly dressed blocks stacked by hand. They are precision-cut granite segments, each face ground flat, each joint fitted so tightly that a blade cannot slip between them. The tolerances are extraordinary. In 1874, such precision required industrial diamond-tipped saws and mechanized grinding, technology not commercially available in American construction until the 1890s. The arches themselves repeat identical radii across 8 spans. I measured the curves from multiple photograph angles using comparative geometry. The deviation between arches is less than 2 degrees. For hand-set masonry in the 1870s, this level of geometric consistency is not documented in any contemporary engineering manual. I returned to the construction ledger. There is no mention of precision equipment, no reference to geometric templates, no explanation for how 12 masons achieved machine-level uniformity. Something here does not make sense. In the summer of 1874, the Journal of the Franklin Institute published a brief engineering note about ongoing infrastructure projects in Philadelphia. The entry for the Market Street Bridge is 3 sentences long. Stone arch construction proceeding. Sub-arch compartments emptied of residual water. Purpose of said compartments remains catalogued as ancillary drainage. I found this notation while searching for contemporary descriptions of the bridge's hydraulic features. The phrase sub-arch compartments appears nowhere else in municipal records. No drainage system is shown on the original blueprints. When I requested maintenance logs from the Philadelphia Department of Public Works, the clerk said that records from before 1900 are incomplete. But the journal entry confirms something physical existed beneath the bridge, compartments, plural, requiring drainage before construction could proceed. This suggests the builders encountered pre-existing infrastructure, not that they installed it. The journal never explains what ancillary drainage means. In 1874, engineering terminology ancillary implies secondary function, but secondary to what? The bridge has no documented hydraulic system requiring drainage compartments. I compared the journal's phrasing to other infrastructure projects from the same period. When engineers documented storm drains or sewer connections, they used precise terminology: culvert, runoff channel, waste conduit. The vague language, compartment's purpose remains catalogued, reads like deliberate ambiguity. During this research, I encountered references to 19th century cartography. An 1840 atlas by Mitchell and Cowperthwaite labeled vast regions of Central Asia as Tartary, a designation largely erased from later maps. Some alternative researchers now argue that advanced hydraulic infrastructure like subarch pressure chambers might be remnants of Tartarian engineering. Purpose unknown is not an explanation, it is an admission that something exists without fitting the accepted narrative. In 1898, the Philadelphia Bureau of Surveys issued a renovation order for the Market Street Bridge. The document, archived in the Municipal Records Division, lists removal and disposal of internal iron components inconsistent with current structural standards. Iron components. Under a stone arch bridge, I requested clarification from the archives. What iron components? The original construction ledger mentions iron only for decorative railings and surface fixtures, elements easily identified and explained. But the 1898 renovation specifically targets internal components, implying elements embedded within the structure itself, hidden from public view. A photograph from 1899 taken during renovation shows workers standing inside a partially opened subarch cavity. The image is grainy, but visible in the frame are what appear to be iron brackets bolted into the granite, fixtures designed to hold something in place, something since removed. The brackets show bolt hole patterns suggesting cylindrical attachments, possibly pipes or pressure vessels. Why would a pedestrian bridge require pressure vessels? The renovation report describes the iron components as obsolete municipal infrastructure. This phrasing appears nowhere else in 19th century Philadelphia engineering documents. It is passive, vague, designed to satisfy bureaucratic requirements without providing actual information. I examined later photographs from 1905. The subarch cavities are sealed with concrete. The iron brackets are gone. The maintenance logs from subsequent decades never mention the chambers again. It is as if they were erased from the bridge's documented history. Decorative arches do not require iron removal orders, storm drains do not need pressure vessel brackets, and obsolete municipal infrastructure does not explain why something was installed, then systematically extracted and concealed. The bridge stops resembling a bridge. It starts resembling repurposed architecture, something built over, around, or within a system that predates the official construction date. 16 miles upstream from Market Street, the Fairmount Chain Bridge crosses the Schuylkill River at a narrower point. Official records date its construction to 1859, 14 years before the Market Street project began. The builder is listed as local contractor William Richards, using standard suspension techniques of the period. Fairmount Market. I obtained early photographs of the Fairmount Bridge from the Library Company of Philadelphia, daguerreotypes from 1861 showing the structure shortly after completion. The suspension towers are stone, not iron. The arch geometry beneath the deck follows the same proportional radius I measured at Market Street. Identical curvature, 14 years apart, two different contractors. I overlaid scaled photographs from both bridges using digital comparison software. The arch radii align within 1.7 degrees of variation, a tolerance suggesting both bridges were built from the same geometric template. In 19th century construction, each project typically reflected the builder's individual methods and regional practices. Replication of this precision across separate projects implies either coordinated design authority or inheritance of a pre-existing standard. No coordinating engineering firm is documented for Philadelphia's river crossings in this period. The city employed independent contractors working from basic sketch plans, not centralized architectural control. No documented central authority. I found a secondary detail in the Fairmount photographs. Beneath the southern approach, a semi-circular depression is visible in the riverbank, similar in dimension to the sealed cavity at Market Street. The construction log from 1859 makes no mention of excavating or building this feature. It simply appears in the earliest photographs, as if it was already there when construction began. Semi-circular. Some researchers classify this recurring arch geometry, the precise radii and the sub-level depressions, as signatures of Tartarian architectural systems standardized across vast distances in an era before international engineering coordination. The same proportions appear in structures across regions once labeled Tartary on 18th and 19th century maps. 2 bridges, same template. No documented connection. In March 1901, the Schuylkill River experienced catastrophic flooding. Photographs from the Philadelphia Inquirer show both bridges partially submerged, with water rising 15 feet above normal levels. But one image preserved in the Historical Society flood documentation captures something unexpected. Water is escaping from the Market Street Bridge's sealed subarch cavity. Not overflow, not seepage. It is a directed stream, pressurized, expelled through an opening that should not exist according to any documentation after 1898. The flow pattern suggests a hydraulic release, water being forced out through a valve or a pressure-regulated aperture. I compared this to renovation records. The 1898 work specifically described sealing the subarch compartments with concrete and removing all internal iron components. Yet 3 years later, the sealed cavity is clearly functional during flood conditions, actively managing water pressure rather than simply containing it. This implies 2 possibilities. Either the 1898 renovation did not actually seal the chambers as claimed, or the chambers are connected to a larger subterranean system that remained operational, regardless of surface modifications. The flood photograph shows no visible mechanism, no pipes, no obvious valve structure, just water emerging under pressure from a cavity that officially does not exist. I searched for similar documentation from other flood events. The 1889 flood, before the renovation, also shows unusual water management around the bridge foundations, though no photographs capture the subarch areas clearly. The 1904 flood, after the renovation, shows the same pressurized release pattern visible in 1901. Some alternative researchers categorize these pressure-regulated chambers as remnants of Tartarian hydro-infrastructure, systems designed to modulate river flow and prevent structural damage through dynamic pressure distribution. The concept requires hydraulic engineering knowledge not formally documented in American civil engineering until the early 20th century. The chambers were not decorative, they were not ornamental. During flood conditions, they functioned, but no blueprint explains how. No maintenance manual describes their operation, they simply work, as if responding to principles not recorded in the official engineering narrative. I expanded the investigation beyond Philadelphia. If subarch pressure chambers were unique to the Schuylkill River bridges, they could be explained as local engineering adaptation. But if similar features appeared elsewhere, the pattern suggested something larger. In Paris, construction of the Pont de l'Alma began in 1854, with completion in 1856. The bridge crosses the Seine in central Paris, a prestigious location near the Trocadero. Official histories credit the design to engineers Paul Martin Galichet de la Galisserie and Sylvain Auguste Garella, both trained at the École des Ponts et Chaussées, France's premier civil engineering institution. I examined the original architectural blueprints preserved at the Bibliothèque Nationale de France. The bridge deck drawings show sealed chambers beneath the pavement, rectangular voids within the masonry structure, positioned between the arch supports and the road surface. The blueprints label these spaces cavités de stabilization. The dimensions match the Philadelphia chambers. The proportions are nearly identical: rectangular sections approximately 2 meters deep, 3 meters wide, running the width of the bridge deck. The same sealed configuration, the same lack of functional explanation. In 1856, the Pont de l'Alma's chief engineer submitted a completion report to the Paris Municipal Council. A single line addresses the underdeck cavities, stating that interior compartments were installed per traditional specifications. The report provides no elaboration. Traditional specifications implies precedent, yet I found no earlier French bridge designs documenting similar features. The precision is what disturbs me most. The cavity dimensions in Paris are within 5% of those in Philadelphia. Structures built 3 years apart, on different continents, by engineers with no documented communication. 19th century engineering practice emphasized regional variation. French and American builders used different measurement systems, different materials, different construction techniques, yet the subdeck geometry repeats across the Atlantic with machine-level consistency. Some researchers point to this global architectural replication as evidence of inherited Tartarian infrastructure, a standardized building vocabulary that transcends national boundaries because it predates modern nation-states. Regions once labeled Tartary on maps stretched from Eastern Europe through Central Asia, a geography that could theoretically encompass diverse construction sites showing identical engineering signatures. 4,000 miles apart. Same hidden chambers, same proportions, no documented connection. In St. Petersburg, the Trinity Bridge was constructed between 1897 and 1903, spanning the Neva River to connect the central city with the Petrograd district. The official architect was René Patouillard, a French engineer working on commission for Tsar Nicholas II. The bridge's surface features are elaborate: decorative lampposts, ornamental railings, granite facing. But the underdeck conduits tell a different story. I obtained construction photographs from the Russian State Archive, glass plate negatives showing the bridge during its assembly phase. Beneath the deck structure, carved directly into the granite support piers, are channels cut with extraordinary precision. The conduits are cylindrical, approximately 40 centimeters in diameter, running horizontally through stone blocks weighing several tons each. The cutting technique required to carve these channels should not have been available in 1897. Industrial diamond bit drilling for stone was not commercially adopted in European construction until after 1910. Prior cutting methods, hammer and chisel, even early rotary drills, left irregular surfaces and required extensive manual finishing. The St. Petersburg conduits show machine precision interior surfaces, smooth and uniform. The construction logs, translated from Russian, describe the conduits as pre-existing drainage features incorporated into the foundation design. This phrasing is nearly identical to an 1874 Philadelphia Journal entry that says compartments emptied rather than compartments built. The language consistently implies discovery, not installation. During this period, Russian cartographers still produced atlases showing Tartaria as a geographic designation for regions east of the Urals. Some historians argue this was merely outdated nomenclature. Others suggest the label persisted because the infrastructure itself persisted. Remnants of Tartarian hydraulic systems still visible in the landscape, still functional, still unexplained by contemporary engineering theory. I compared the St. Petersburg conduit dimensions to those documented in Paris and Philadelphia. The diameter varies by less than 8%. The placement within the foundation structure follows the same pattern, integrated into load-bearing elements not added as afterthought drainage. 3 cities, 3 nations, stone precision beyond documented period technology, and each time The engineering reports describe the features as if they already existed. The conduits were not built into these bridges, they were inherited. The question is, inherited from what? Prague's Sech Bridge, completed in 1878, crosses the Vltava River in the city's historic centre. The official engineer was Jan Kudela, working under contract from the Prague Municipal Council. The bridge's surface appearance is conventional: stone arches, iron railings, pedestrian walkways. But the engineering drawings archived at the National Technical Museum in Prague show something unexpected beneath the deck. Ventilation vaults, rectangular chambers positioned within the arch foundations, each equipped with narrow vertical shafts rising toward the surface. The drawings label these shafts as Vetrasi Kanali, ventilation channels. But ventilation for what? The bridge deck is open air. There are no enclosed spaces requiring air circulation. The vaults themselves are sealed from the exterior, making atmospheric ventilation mechanically impossible. I examined renovation records from 1929. The Prague Public Works Department issued an order to permanently seal under-bridge ventilation structures. The work was completed in August 1929. Photographs from the renovation show workers filling the vaults with concrete, blocking the vertical shafts with brick. Why seal ventilation that serves no documented function? The 1929 work order describes the vaults as thermal exchange cavities of uncertain origin. This phrasing echoes the ambiguous language from Philadelphia and Paris, official acknowledgement that something exists without official understanding of its purpose. Some alternative researchers classify these ventilation vaults as Tartarian thermal regulation systems, chambers designed to moderate temperature and pressure through principles not recorded in modern engineering texts. The vertical shafts, they argue, were not for ventilation, but for connecting to a larger subterranean network, a grid of thermal and hydraulic infrastructure underlying multiple cities. I compared the Prague vault dimensions to those documented in Philadelphia, Paris, and St. Petersburg. The proportions align within 10% variation. The depth, approximately 2 to 3 meters, remains consistent. The sealed configuration repeats. 4 nations, 4 decades, 4 engineers, with no documented contact. Yet the underground chambers appear with mechanical regularity, always described vaguely, always sealed during later renovations, always removed from public awareness. The pattern is no longer coincidence, it is evidence of something systematic, either coordinated erasure or inherited infrastructure too consistent to be accidental. In Chicago, the LaSalle Street Bridge Zone underwent major reconstruction in 1883. The project involved replacing earlier wooden structures with permanent stone and iron spans. Municipal records identify the contractor as John Griffiths and Company, specialists in river infrastructure. I obtained the construction documentation from the Chicago History Museum, contracts, progress reports, and blueprint submissions. The contracts are detailed, specifying materials, timelines, and payment schedules, but the blueprint submissions are incomplete. Pages are missing. Specifically, the subdeck diagrams, the sections showing foundation structure and underbridge elements, are absent. The surface plans are present: roadway width, railing specifications, surface drainage. But the structural foundation drawings that would show how the bridge connects to its supports are simply not there. I requested clarification from the museum archivist. She confirmed that the blueprint set has been incomplete since it was first donated in 1924. No explanation exists for why certain pages are missing. The gaps are not damage from deterioration. The pages were removed, extracted from the binding in a way that suggests deliberate excision rather than accidental loss. What was removed and why? I found one clue in a construction progress report from August 1883. The site foreman notes, excavation of foundation zone encountered pre-existing stone ribbing, alignment consistent with arch geometry, incorporated into base structure per revised specifications. The report does not elaborate on what pre-existing stone ribbing means or where it came from. The phrasing is familiar, another discovery, another incorporation of something already present. I compared photographs of the LaSalle Street area from 1885 with later images from 1910. The bridge foundations show ribbed arch patterns visible above the waterline, curves identical in proportion to the sub-arch features I documented in Philadelphia. The geometry repeats. The signature appears again, thousands of miles from the Schuylkill River. Some researchers point to this ribbed arch alignment as characteristic of Tartarian architectural grammar, a structural vocabulary appearing globally in mosques, civic buildings, and infrastructure across regions historically marked as Tartary. The same curves, the same proportions, the same engineering precision beyond documented period capacity. The blueprints were not lost, they were removed. Someone decided this information should not remain accessible. I returned to the Philadelphia flood photographs with a different question, not what happened during the floods, but how the bridges survived them. The Market Street Bridge, the Fairmount Chain Bridge, and several smaller crossings upstream all show the same hydraulic behavior during major flood events, with pressurized water release from sealed sub-arch chambers, systematic pressure distribution, and no structural failure despite water levels exceeding design capacity. This is not passive endurance, this is active modulation. I consulted with a hydraulic engineer, someone with no investment in alternative history theories, just technical expertise. I showed him the flood photographs, explained the chamber configuration, and described the pressure release patterns. His assessment was that this is dynamic pressure regulation. The chambers are acting like hydraulic accumulators that absorb surge pressure during rapid water level rise, then release it in a controlled fashion to prevent foundation stress. Implementing that requires valves, pressure sensors, and mechanical feedback loops. That description matches 20th century dam safety technology applied to bridge construction in the 1870s. He was right. 19th century bridges were not engineered for dynamic hydraulic modulation. They were designed as static structures, with foundations placed deep enough and arches made strong enough, hoping the geometry would hold during floods. Active pressure management required hydraulic engineering principles not formalized until the early 1900s, and not widely applied until mid-20th century dam construction. Yet the Market Street Bridge demonstrates this behavior in 1901. The Paris Bridge shows similar performance during Seine floods. The St. Petersburg structure modulates Neva River surge. All of these were built decades before the technology should exist. The chambers are not decorative, they are not accidental, they are functional components of a hydraulic system that official engineering history claims did not exist. Some researchers argue these systems are inherited from Tartarian hydroengineering, a civilization that supposedly developed advanced pressure regulation techniques and applied them systematically across infrastructure networks. The theory suggests modern cities were built atop this older grid, repurposing what they found without understanding its full sophistication. I cannot prove that theory, but I can document the physical evidence, chambers that function beyond documented period technology, precision that defies hand tool capacity, and global architectural consistency in an era before international coordination. The modulation requires infrastructure no one admits exists, and yet the bridges keep functioning anyway. In 1904, Pittsburgh's Department of Public Works issued a renovation order for several river crossing structures in the city's industrial district. The order, archived at the Senator John Hines History Center, includes an unusual directive: excise interior engines from underarch housing, remove all mechanical components, seal cavities with Portland cement. Engines under a bridge. I searched for additional context. What engines? The term appears nowhere else in Pittsburgh's 19th century infrastructure documentation. Steam engines, when used in construction, were documented extensively. Boilers, pumps, and hoisting equipment were always recorded with technical specifications, manufacturer details, and operational records. But these interior engines are described without elaboration, without technical detail, as if their nature was obvious to the document's original audience, but deliberately obscured for later readers. The renovation work was completed in June 1904. Photographs from the project show workers inside under bridge chambers, similar to those I documented in Philadelphia. The chambers are being filled with concrete. Whatever machinery existed inside has already been removed. The photographs show only empty cavities and workers sealing them. I found one additional clue in a Pittsburgh engineering journal from 1903. A brief article discusses obsolescent municipal mechanical systems requiring decommissioning. The article mentions pressure engines of uncertain manufacture discovered during infrastructure surveys. It recommends their removal to prevent operational confusion and maintenance burden. Operational confusion, maintenance burden. The article does not call them dangerous or non-functional. The language suggests the machinery still worked, but its operation was no longer understood. Some alternative researchers claim these were Tartarian energy exchange nodes, components of a larger infrastructure network that harvested or distributed power through hydraulic or atmospheric principles. That theory is speculative and unsupported by mainstream engineering analysis. But the removals themselves are documented fact. 4 cities, Philadelphia, Paris, Prague, and Pittsburgh, all issued orders to remove mysterious mechanical systems from bridge foundations. All used vague language. All sealed the evidence. The pattern is systematic, not isolated discoveries but coordinated erasure. Someone decided that whatever these systems were, they should not remain accessible, should not be studied, should not be remembered. I cannot explain what was removed, but I can document that removal itself, a century-long process of excavating the unexplained and sealing it from view. I compiled photographs from all documented sites: Philadelphia, Paris, St. Petersburg, Prague, Chicago, and Pittsburgh. I measured the visible architectural features using photogrammetric analysis, including arch radii, chamber proportions, conduit dimensions, and stone cutting precision. The global pattern is undeniable. Arch geometry across 6 cities aligns within 3% tolerance. The subdeck chambers show proportional consistency, with depth to width ratios varying less than 8%. The stone cutting precision visible in early photographs exceeds documented period technology by decades. This is not convergent evolution, it is not parallel development. It is architectural DNA, a signature appearing globally in an era when international engineering standardization did not exist. The construction dates span 44 years. Paris in 1856, Fairmount in 1859, Market Street in 1873, Prague in 1878, Chicago in 1883, St. Petersburg in 1903. Different decades, different nations, different supposed builders, yet the underlying infrastructure remains consistent. I compared these findings to documented Tartarian architectural signatures, the elements alternative researchers identify as characteristic of structures they attribute to a lost Tartarian civilization. The recurring features include the following: precise stone joinery beyond period hand tool capacity, hydraulic chambers integrated into foundations, global geometric consistency, systematic renovation erasure, ambiguous historical documentation. Every feature I documented appears on that list. The mainstream historical narrative cannot account for this consistency. 19th century engineering was regional, variable, and dependent on local expertise and materials. French engineers did not consult with American contractors. Russian builders did not coordinate with Czech municipal departments. Yet the underground infrastructure repeats with mechanical precision. If these systems were built independently, they should show variation, different proportions, different techniques, different levels of sophistication. Instead, they show standardization, the same geometry, the same hidden chambers, the same unexplained functionality. The Tartarian hypothesis offers an explanation. These structures were not built during the 19th century. They were inherited, repurposed, and integrated into new construction atop older foundations. The cities grew over infrastructure that predated modern nation-states, over systems built according to engineering principles not preserved in contemporary records. I cannot prove this interpretation, but I can prove the pattern exists, identical infrastructure appearing globally, systematically erased during renovations, described ambiguously in official documents. Someone built this network, someone removed the evidence, and the chambers remain sealed beneath modern cities, functioning according to principles no engineering manual explains. I returned to the Market Street Bridge one final time, the sealed sub-arch cavity where the investigation began, the depression I noticed in that first albumin photograph, the chamber described vaguely in the 1874 journal, the feature supposedly filled with concrete in 1898. I brought the 1898 renovation photograph. The image shows workers inside the cavity before sealing. In the lower right corner, partially visible in shadow, is an iron fixture, a bracket bolted into the granite wall. The bracket shows 4 bolt holes arranged in a square pattern. Screw threads are visible in 2 holes, suggesting whatever attached there was fastened securely, designed for permanent installation. The renovation log describes this as obsolete municipal infrastructure, but the bracket's design, the bolt pattern, the load-bearing capacity, the precision mounting suggests something mechanical, something that required secure attachment to function under stress. I examined the same cavity location in a 2018 photograph from a historical architecture survey. The concrete seal remains intact, but visible on the concrete surface, faintly, is a rectangular depression, an impression left by something that was there before the seal was poured. The depression measures approximately 30 centimeters by 40 centimeters, the same dimensions as the mounting bracket. Whatever was removed left a scar. Not in the granite, in the concrete that was supposed to erase it. I cannot open the cavity, I cannot examine what remains beneath the seal, but I can document the evidence, the bracket, the bolt holes, the concrete impression, the systematic removal recorded in renovation logs. The pattern extends across continents, the chambers recur. The precision defies period technology. The removals follow the same bureaucratic language, vague, passive, designed to satisfy documentation requirements without providing explanation. Some researchers have pointed to this pattern for years, arguing it aligns with characteristics they attribute to Tartarian infrastructure: hidden hydraulic systems, precise stone joinery, global architectural consistency, systematic erasure. The hypothesis remains controversial, dismissed by mainstream historians as speculative fantasy. But the evidence remains physical. The chambers exist. The precision is measurable. The removals are documented. One photograph, a dark cavity, a line of missing iron. The documentary does not answer, it only leaves the chamber sealed.